Today's lesson will be on Kirchhoff's rules. The junction rule states the total current directed into a junction must equal the total current directed out of the junction. So in other words, let's say we have 7 amps coming into a junction point, and 5 leaves one direction and 2 leaves the other direction. So what goes in has to equal what goes out. It's kind of common sense. The loop rule expresses conservation of energy in terms of the electric potential and states that for a closed loop, the total of all the potential rises is the same as the total of the potential drops. So let's look at it here. If you're going in this direction, the battery raised the potential by 12 volts, and it lost 10 volts going across this resistor and 2 volts going across this resistor. So it lost 12 volts, but it gained 12. So the loss was equal to the gain. And here's the rules written once again. And this is the formal definition. The junction rule: the sum of the magnitudes of the currents directed into the junction equals the sum of the magnitudes of the current directed out of the junction. And the loop rule: any closed circuit loop, the sum of the potential drops equals the sum of the potential rises. Alright, so here's an example using the loop rule. We have a circuit here, and it has 2 batteries and 2 resistors. We know that voltage drops must equal voltage gains. So what actually is a drop? Drops occur across resistors in the direction of current. So if we choose the direction of current going this way, which is arbitrary, and we go across the resistor, we have a potential drop. When we go across a battery from high to low, it's also a drop. And rises occur if you go across a resistor in the opposite direction you chose as being positive, or the direction of current. So for example, let's say we chose clockwise as being the direction of the current. If we end up going across this in this direction, for example, then it would be a rise. And if you go from the negative side of a battery, like say you're going this way, and you go from the negative side to the positive side, that's a rise. So let's see if we can apply that. Most people start problems in the upper left-hand corner and go this direction. The choice of the current direction is kind of arbitrary, so I'm going to choose it as being clockwise. If I was wrong, it would show up in the math. So there we go. I'm going to say that potential drops have to equal the potential rises. Now, why are each of these drops? Because if we choose current as going this direction, you're going across the resistor in the direction of the current, so it's a drop. So I times 12 ohms, because voltage is equal to I times R. And once again, this is a drop, because you go from the high side of the battery to the low side. Once again, this is a drop, because you go through a resistor in the direction of current. And that must be equal to the rise. And here it's a rise because you go from the negative side of the battery to the positive side of the battery. So we have all the drops have to equal all the rises. And then you can just solve for I, 0.9 amps. Most simple resistor circuits can be solved without use of Kirchhoff's rules. Many of the problems you'll see in the AP exam you could do without Kirchhoff's rules, but you should understand the idea behind Kirchhoff's rules because there'll be questions pertaining to that. There's a real advantage of Kirchhoff's rules when there's more than one voltage source. So one such example is this problem here, where there's actually more than one voltage source. You have the battery and an alternator attached to the lights. So there's 2 potential voltage sources in parallel. So how do you actually solve Kirchhoff rules problems? There's a strategy that you should follow. You should draw the current in each branch of the circuit. Choose any direction If your choice is incorrect, the value obtained for the current will turn out to be a negative number. In other words, indicating that you chose the wrong direction. Mark each resistor with a positive at one end and a negative at the other end, and in such a way that's consistent with what you chose for current. Outside a battery, the conventional current is always directed from the higher potential. Mark that part positive, to the lower potential, mark that at negative. You apply the junction rules and the loop rules, and you obtain independent equations, and you have just as many independent equations as you have unknowns. And you solve these simultaneously for the unknown variables. And we'll do a couple of these problems in class. Alright, also in class we're going to have to understand how to use different meters to measure voltage and current. And I want to spend a moment and explain that. Ammeter will obviously measure current. So how should we place that in a circuit? We actually have to interrupt the circuit, have the current go through the meter, and then back out. So with that in mind, we have to have the internal resistance of this meter be extremely small so it doesn't affect the current going through the circuit. And to measure voltage, voltage is measured between 2 points, and that's placed in parallel. And if you think about it, the internal resistance here must be extremely high, because if this was a low internal resistance, now the meter, all the current would choose to go through the meter instead of through the resistor. And that's basically how we place ammeter and voltmeters in circuits.